And this section is all about understanding BGP attributes. So when you look into internal gateway protocols, EIGRP or OSPF, what they're looking for is determining what is the best path, and that's typically based off of the idea of the physical interface types, right? The speed of the interface. We're looking at bandwidth, and EIGRP looks at delay that we have to deal with, right? So those are all determining what's the best path based off of that particular metric, if you will. BGP does not use a metric of bandwidth. It utilizes these, what we call path attributes, and these attributes are used to determine what is the best route in a BGP environment. None of them, by default, have anything to do with things like bandwidth or delay, okay? So you're going to see some of these attributes we have, and they're categorized in two main types. We have what they're called well-known attributes, and a well-known attribute has to be essentially understood by any implementation of BGP. I don't care if it's on a Cisco router or a Juniper router or a Brocade switch that we have. If it's running BGP, it has to know what these well-known attributes are. We then also have what they call optional attributes. And optional attributes are, as the name implies, optional, right? I might use them, I might not use them. And you're going to see they then break up those different well-known attributes and what they call well-known mandatory attributes and well-known discretionary attributes. A mandatory attribute has to be present in the BGP update, where a discretionary attribute doesn't have to be there. Likewise, when we look at optional attributes, you'll see that we have what they call transitive and non-transitive attributes. A transitive attribute would say, if I don't know what that attribute is, I don't use that optional attribute, I'm going to leave it in the routing update and send it off to the next hop route. Maybe they can use that attribute. Versus a non-transitive attribute. A non-transitive optional attribute says, if I don't know what it is, I'll throw it away, that particular attribute, and send off an update to my next hop neighbor without having that particular attribute a part of it. Okay, so you're going to see that we have these different attributes that we have. And we're going to go through quite a few of these attributes here in BGP. We mentioned the well-known attributes have to be there. Okay, everyone has to know what they actually are. But you're going to see two different types, like we said. There's well-known mandatory attributes. They have to be in the update versus a discretionary attribute that does not have to be in there. It could or could not be in there. Okay. They show you different mandatory well-known attributes. One of them is known as the origin code. And the origin code essentially tells us, how did this route get into BGP to begin with? You're going to see there are three different origin codes we can have. There's a lowercase I. It says the route originated in an IGP. I want you to think, rather than it originated in an IGP, instead think of someone using the network command in BGP to advertise a route outbound, okay? That's typically when it shows up as an I, versus a lowercase e. And the lowercase e means the route originated in what they call the external gateway protocol. Before BGP, there was a protocol called EGP, and what you would do is you would redistribute EGP routes into BGP, and therefore would show up as a little e. And last but not least, there is a question mark, or what they call incomplete when you look at it in BGP. They show the route was redistributed into BGP from some other routing protocol. So this is using the redistribute command, redistributing routes from OSPF or EIGRP or directly connected routes or static routes. Those would show up as a question mark by default. Okay. And when we look in the BGP table, you'll see the origin code is way off to the right-hand side. It'll have a little lowercase I or a little lowercase e or question mark on it, way on the right-hand side of that route in that path. You then have what they call the autonomous system path. And the AS path is almost like a hop count, if you will. How many autonomous systems has this particular route gone through? And therefore, how many autonomous systems do we have to go through to get back to that destination network? Okay, so it's just a list of these autonomous systems. And every time we send a BGP route out to an external BGP neighbor, meaning to a different autonomous system, what I will do is prepend my own autonomous system number to this path. okay? And we're gonna see how that works in just a little bit. And then we also have the next hop attribute. Very important attribute that we utilize within BGP is this next hop. And they show us the IP address of the next hop router. Not really, okay? It is the IP address of the next hop autonomous system by default. As you will see, when we learn a route from an external BGP neighbor, by default in BGP, as I advertise that to an internal BGP peer, we do not change any of these attributes, okay? So this next hop is important because it's how we do what they call the recursive lookup in BGP. When we look at a BGP route, you'll never see that a BGP route says, to get to this network, go out this interface, right? What they have to do is they're gonna see, to get to this route, go to this next hop address. I then have to do this recursive lookup. How do I reach that next hop address? And I should then find an OSPF or an EIGRP route, some internal gateway protocol route that tells me how to reach that next hop address and what's the best interface to go to that next hop address, okay? So very important for us is what we call this next hop attribute in BGP, allowing us to do that recursive lookup. We have some what they call well-known discretionary attributes. And like we said, everyone needs to know what these are, but they may not be a part of the routing update. Kind of depends whether or not someone wants to change things. One of them is known as the local preference. A local preference is used for what's my best path out of my autonomous system, okay? It allows us to be able to go through and have an interface. Maybe I want a primary provider and a backup provider, right? If I go through and utilize a local preference value, I can say whoever has the highest local preference value is my preferred path out of my autonomous system. We have what is known as the atomic aggregate. The atomic aggregate informs the neighboring autonomous system that the originating router aggregated the routes, meaning they summarized those routes, okay? That's what we're looking for. So again, these are well-known discretionary attributes. They may or may not be a part of the BGP update. Like for instance, you may not have had anybody actually go through and do summarization within BGP, and therefore you wouldn't see the atomic aggregate. Likewise, we also have these optional attributes. And we mentioned the difference is that an optional attribute does not have to be supported by all implementations of BGP. And you're going to see that they've got optional transitive attributes and optional non-transitive attributes. We mentioned the transitive attributes would say, if I don't know what that attribute is, I'm going to leave it in the BGP update and send it off to my next hop neighbor. Essentially saying maybe they know what that attribute is and they can use that. You're going to see that if they don't recognize it, they will mark that as a partial, they mark what they call the partial bit. Okay, meaning that there's someone along the line that did not understand an attribute in that BGP update. Okay. And then we also have optional non-transitive attributes. Essentially says, I'm going to send it to the next hop router, but if they don't know what it is, they're going to drop that attribute from the BGP update altogether. Okay, they don't know what it is, they don't use it, so they're going to throw it away. They will not send it off to the next hop neighbor. And typically it's because that attribute is only used by my next hop neighbor. Anyone past that neighbor wouldn't understand how to use it anyway. Okay. And they show recognized optional attributes are propagated to their neighbors based off their meaning. They're not constrained whether or not it's a transitive or a non-transitive attribute. Okay, so it's really about what type of attribute it actually is. And you're going to see that we have the optional non-transitive attributes. The only one that they have is what is known as the multi-exit discriminator, or the MED value. Now, I just want to make sure you guys realize this. When you're looking at a BGP table, this MED value actually shows up as what they call the metric, okay? And the idea is it's typically used when you've got multiple links to the same service provider, okay? Imagine that I've got my autonomous system and I've got a link that goes out, multiple connections out onto the same ISP. We'll call it ISP number one out over here, okay? I can, again, if I'm trying to say I want a primary path and a backup path, going out of my autonomous system, we'll call my autonomous system 65,000 here. I can use local preference. The higher the local preference value, the more preferred that route is going to be. So what I can do is, as I learn routes from ISP number one, anything that comes in on my primary link, I can set a local preference value on that. In this case, setting that local preference to be 150. As I receive routes coming in on my backup link, I can set my local preference down to 50 on that. So what that does for us is it means that my local autonomous system 65,000 is going to prefer all the routes going out to ISP number one in this direction across my primary path. Well, likewise, we want the return traffic to come across that primary path as well. So when I advertise my network, let's just give an example here. Let's say I'm advertising, again, private address, I know, but let's say I'm advertising the 10.0.0.0/8 network outbound to my provider. And I'm advertising that on both of these links, right? They need to know how a backup route to be able to get there. I'm going to set this multi-exit discriminator value. And when you look at the med value, we said the higher the local preference, the more preferred that route. Med is the exact opposite. The lower the multi-exit discriminator value is the more preferred route. So when I advertise this 10 network outbound to my service provider, I can set a med value of, let's say, 50 on this particular route. And as it goes out on my backup link, I can set that med value to be 100, for instance. That tells ISP number one that the best path back into my autonomous system, 65,000 out over here, is this top link, my primary path. Okay, so it's not about influencing my routing behavior, but influencing the routing behavior at the service provider. Now, you only look at med if you're receiving the exact same route from the exact same autonomous system. In this case, ISP number one is receiving this 10.0.0.0/8 network from the same autonomous system, 65,000. Right? So it would actually go through and compare those med values at that point in time. And why they considered it a non-transitive attribute. ISP number one, if they sent it out to any other service provider, that service provider would say, well, that doesn't make any sense. I'm only receiving one route from you anyway. Right? So there's no reason for that next autonomous system to actually receive the med value. We have optional transitive attributes. Right? Like I said, these transitive attributes would remain as a part of the BGP update even if ISP number one does not know what that attribute actually is. And you'll see one of them is known as the aggregator. It specifies the IP address and autonomous system number of a router that performed summarization, or route aggregation. Okay. And then we also have what they call community strings in BGP. And these community strings can do all sorts of different things. You'll see that we have what they call standard and extended community strings. They're essentially used for tagging a route. Typically, when you look at a community string, you'll see a number with a colon, then another number, like 300:150, okay? And the way you typically read this community string is whenever this route reaches autonomous system number 300, I want you to do whatever tag number 150 does for us, okay? Service providers utilize those tags to be able to set their own attributes in their own autonomous system. Like maybe what I want to do within here is, let's give you an example of why you might want to use something like this. If med can only be sent between my one service provider, what happens if I've got multiple service providers? So now let's imagine that I've got, again, 65,000 as my autonomous system, and I've got my network 10.0.0.0/8 here, but I've got multiple service providers. And I might want to influence the idea of how ISP number 2 reaches my 10 network. Okay? One of the things that you're going to typically see as far as our BGP path selection process is that it would typically utilize the shortest autonomous system path, going right into autonomous system number 65,000, rather than going through ISP number 3, then to ISP number 1, then into my autonomous system 65,000. Okay? So one of the things that we can do within here is I can set an update. As I send my route for this 10 network outbound to ISP number 1, I can set a community string like 2:150 on this. ISP number 1 would advertise that community string outbound. Eventually is learned out over here at ISP number 2. And ISP number 2 can have an access list, they call it a community string access list, that matches this community string and then sets information like a BGP attribute. They might utilize this to say, hey, once it reaches service provider number 2 over here, what my tag of 150 is going to do is to set the local preference of that route to be 150. So now the idea is that ISP number 2 has just preferred that the best route into my autonomous system is through ISP number 3, rather than going through directly to me and using my backup link. Okay, so it's essentially a way of being able to tag a route. Now these tags can do all sorts of different things. You'll see it really kind of depends on how you're using BGP. We're talking right now in the idea of utilizing it for internet routing. But if you start dealing with the idea of like an MPLS core, MPLS uses these community strings for what they call a route targets. We have what they call import and export route targets in MPLS. And they're used to be able to say, as I receive this route, can I import that route into a VRF's routing table? And so they're used for a lot of different things that could potentially be done within here. But just give you an example how that tag actually works within. So we're going to kind of go through one at a time and discuss some of these major attributes that we deal with. We mentioned the idea that autonomous system path attribute. It is essentially nothing more than a list of all the autonomous system numbers that this route or this prefix or this path that we have in BGP has gone through. Okay, they show originally when I'm advertising in BGP, the autonomous system path attribute is empty. There's no autonomous system numbers in that. It's not inserted until I send it to an external BGP neighbor. Okay, you'll see the AS number of the sender is prepended to the AS path when the routing update crosses an autonomous system path boundary or not an autonomous system boundary. Give you kind of an example. Let's say that I've got, I'm going to use a different color here. Let's say that I've got autonomous system 65,000, and it's connected to autonomous system 65010, and that's connected to 65020, and that's connected to 65030, and maybe that even has another connection back in this direction. So as I advertise my route, and I send it outbound to my next top neighbor or my external BGP peer, what I'm going to do is prepend my own autonomous system number to that AS path. Well, like we said, it starts off as empty, right? So what you're going to see in this case is my network, the 10.0.0.0/8 network, and it'll have an autonomous system path that you got to reach autonomous system 65,000. And that's really just telling autonomous system 65010 in this case that I've got to go through one autonomous system to get back to that 10 network. Now, as they advertise it outbound to their external BGP peers, again, you're going to see them prepend their own autonomous system number to that path. So you're going to see this route now. Is to reach 10.0.0.0/8, you got to go through autonomous system 65010, then eventually 65000 to reach that destination network. As 65020 advertises that route outbound to 65030, again, they will prepend their own autonomous system number to that path. So they'll be advertising to reach the 10 network in this direction. You got to go through autonomous system 65020, then to 65010, then to 65000 in this direction to be able to get there. Right? And if you think of it like a hop count, not how many routers do we have to go through, but how many autonomous system numbers do we have to go through to utilize that particular path. Now, AS 65,000 is also neighbors with 65030 as well. So they're going to advertise this network. Hey, to get to the 10.0.0.0/8 network, you can go directly to 65,000 to get there. And that autonomous system 65030 in this case, they're going to determine which one is the best route. Autonomous system path is one of those things that we eventually look into, assuming that nothing else has been changed. It is normally how we determine what is the best path in BGP. I would rather go directly to autonomous system 65,000 rather than going in this direction and having to go through 3 other autonomous systems to be able to get there. Okay, so it's just simply looking at how many AS numbers do we have in that path to determine what is the best path. They show the receiving of the BGP routing information could use that AS path attribute to determine which AS the information is passed through. It also determines which one is the best route in a lot of cases as well. Okay. Now, we're also going to utilize this to recognize routing loops in BGP. Notice this last bullet. As an autonomous system that receives routing information with its own AS number in the AS path, silently ignores that information. It essentially says, hey, if my AS number is in that AS path, it's a routing loop. So I'm going to drop that route. Okay. So it's used not just to determine what is the best path, but also to recognize routing loops in a BGP environment. So they mentioned the idea in this case, we said anytime I send that out to an external BGP peer, which means one router to another router in different autonomous systems, I'm going to prepend my own AS number to that path. So here we're telling autonomous system number 21 that to get to the 10 network, you got to go to AS number 123. Notice that when the AS 21 sends it out onto AS 37, they prepend their own number to that AS path. Hey, to get to that 10 network, you got to go through autonomous system number 21, then to autonomous system number 123. Autonomous system number 37 would advertise that route outbound in the other direction to its neighbors. And again, they prepend their AS number to that AS path. But now, we mentioned we also use this AS path to recognize routing loops. So when I receive that over here, and I see my own autonomous system number is in that AS path, that's where we're going to deny that route. We're going to say, nope, that's a loop that we see in the network because my own autonomous system number is in that path. The next hop attribute, as they show, indicates the next hop IP address that's used for packet forwarding. What we are going to do is this is what we call that recursive lookup. All of our BGP routes are going to say to get to this network, you need to reach this next hop address. So my recursive lookup is to say, how do I get to that next hop address? That will then tell me what interface I'm going to be using in that case. Okay? So they show us usually set to the IP address of the sending external BGP peer. However, the attribute can be set to a third-party IP address to optimize routing. And we're going to see that in a transit autonomous system. A lot of times we're going to go through and change that to be the local router in our AS. So to kind of give you an example of what's going on within here. Notice we're advertising a network. And it's kind of tough to see because I didn't mention it, but think of this network as the 21.0.0.0/8 network is here in autonomous system number 21. As router number 2 advertises this route outbound to router number 1, they not only add their AS number to the AS path, but the IP address on this interface, which is 10.1 and 0.0.1, is the next hop of this BGP route. Now, router number 1, that is actually considered to be the very next hop router, okay? And they're going to show you this, but I want to make sure that you recognize what happens. Remember when we send it to an internal BGP peer. So let's say we've got it over here. I'm going to call this guy router number 4 because it's not depicted anymore. It's also a part of autonomous system number 123. By default, this next hop attribute is not changed as I send that route from an external neighbor to an internal BGP peer. So when I advertise this route outbound to router number 4 in this case, And you're going to see that the next hop address is still 10.1.1.1. So that means router number 4 needs to have a route on how to reach this IP address to be able to use or advertise that route. However, when I send that route to an external neighbor, in this case, outbound to router number 3, you're going to see that's different. We change attributes as we send those to an external neighbor. My assumption is that autonomous system number 37 doesn't know how to reach this network and therefore wouldn't know how to reach a 10.0.0.1. So what we will do is when I advertise it outbound to router number 3, I'll change that next hop attribute to be a 10.1.0.5, which router number 3 knows how to get there because it's a directly connected network. Okay? Sorry about that. I think they show that here in just a second here. So as I advertise that outbound to another neighbor, it changes that attribute. Now, when is that different? Well, it would be different if everybody was on the same subnet. Now notice in this case right here, router number 2, router number 3, and router number 1 are all on the 10.0.0 subnet. So when router number 2 sends the attribute outbound to router number 1, and again, as far as neighbor relationships, we have a neighbor relationship between router number 1 and router number 2, and a neighbor relationship between router 1 and router 3. But no BGP peering session between router number 2 and router number 3 in this case. So as router number 2 advertises its outbound, notice his own IP address is the next hop address of that route. As router number 1 advertises this outbound to router number 3, notice in this case, we leave that attribute alone. We're assuming that even though you don't have a BGP peering session between router 2 and router number 3 knows how to reach this next hop address because they're in the same subnet. So instead of having to send you like an IGMP redirect, it allows router number 3 to say, if I want to get to the 21 network, I can directly send that to router number 2. They're on the same subnet as I. Now, that is really important when you start looking at the idea of using BGP in a, let's say, a dynamic multi-point VPN scenario, okay? Anytime you're dealing with a multi-point environment like that, you have people that are in the same subnet that don't have direct reachability between each other, okay? So think of a frame relay environment where you have a non-broadcast multi-access environment. DMVPN is where you really see it a lot today. There you go. They even bring it up to the very next stage here. Right? The idea of DMVPN, all of my router on their tunnel interfaces are typically in the exact same subnet. Right? So even though router number 2 is advertising outbound to router number 1, and it says the next hop should be 10.0.0.1. By default, when router 1 sends that information to router number 3, it would leave that next hop attribute to be 10.0.0.1, assuming that because we're all in the same subnet, you should be able to reach a 10.0.0.1. Well, that's not necessarily the case in this environment, right? So what we need to do is they show connectivity is broken and router 3 can't reach the next hop at 10.0.0.1. They don't have a direct connection to router number 2. So in that kind of environment, we want to go through and tune that. Essentially what we're going to do is say, as I advertise outbound to router number 3, I shouldn't leave this next hop attribute alone. I should change that next hop attribute to something that router 3 knows how to reach. In this case, they know how to get to a 10.0.0.2. You've got to send that to me. I can then forward it on to router number 2 because I've got a connection with router number 2. And then we do that by utilizing what they call the next hop self command in BGP. So I want to just go through, kind of show you a little bit about like the BGP table here. And where you see some of these attributes, okay? So this is a BGP table. They've gone through and done a show IP BGP in this case. is a command to look at all of your BGP routes, right? In this case, you might see multiple routes to the same destination. Now, BGP does not load balance, okay? So what they're gonna do is they're gonna find out of routes. In this case, notice right here, we're seeing we have 2 routes to the same network, the 10.1 or the 1.0.0.0 network. Notice they got this little greater than symbol right here. That tells me that this bottom route is deemed as the best route in BGP. And they show that kind of a table of contents over here of what that actually is. Here we get to see the origin code of all of these routes. These are all an I, meaning that someone used the network statement to advertise those outbound. Here we get to see the autonomous system path of the route. You had to go through autonomous system number 200, then to 99, versus through 100, then to autonomous system number 99. We mentioned that the med attribute, okay? The med attribute is also known as the metric in the BGP table. We got a local preference attribute, there's a wait attribute. Here's the next hop, right, of how to actually reach that particular route. So you can see that information in that BGP table. And important to recognize this right here, the path selection process in BGP. How does it use those attributes to determine what is the best route? And you're gonna see that BGP keeps on going until it finds one and only one best route to get to a destination by default, okay? So a couple different things. First off, you're gonna see it excludes any routes with an inaccessible next hop. Let me go back to that picture out over here of the BGP table. We said, we see the next hop address of a route. Notice this little asterisk right here. It tells me, is it a valid route? Okay? And that typically means that I have some path to reach this next hop address. If I cannot reach the next hop address, I cannot use or advertise that route in BGP. It is seen as a non-valid route, okay? So that's the first thing they look for. Can I reach the next hop address? And then I would prefer a route with the highest weight value. Now, the weight value is just for one individual router. It is technically an optional non-transitive attribute, but it's never in any BGP update. I don't send it to any other router, not an internal neighbor, not an external neighbor. It is usually used when I have one single router and I have multiple paths out of my autonomous system. So if this is my AS, I've got one single router, maybe connected to multiple service providers, for instance, right? I can let this local router determine what the best path outbound is, okay? But again, it's never advertised to any neighbor. So it only has significance to that one local router. Well, what happens if we don't have this scenario, but instead what we have is we have another router out over here, and they've got a session in between. And maybe router number, we'll call this router number 1 and router number 2. I've got ISP number 1 and ISP number 2. Maybe what we want to do in this case right here is to prefer our path through ISP number 1. And use ISP number 2 as a backup path to the internet. Well, that's where local preference can be in play. And again, local preference is sent, they show global within the autonomous system. Right? Think of to only internal BGP peers is what I want you guys to think of. So that allows me to say, if I want to prefer the path through a service provider number 1, all the routes that we learn from provider number 1, we will set a local preference to be 150 for those routes. And that is then advertised outbound to router number 2, so that router number 2 can use that local preference. When we learn the path inbound from ISP number 2, we might just leave it alone. It would have the default local preference of 100 for that route. And like they show, we would prefer the highest local preference value. Okay? This ensures that we have an autonomous system-wide policy, essentially, that tell both router 1 and router 2 that my best path out of my autonomous system is through ISP number 1. Okay. The next thing we look at, let's say we got a tie in local preference. It would then prefer routes that were originated by a local router. And what would be the case there? If it was originated by the local router, what we're talking about is to think of the next hop. Will be 0.0.0.0. My own local router advertised this out on a BGP. And it kind of makes sense. Why would I use anybody else's route if I'm the one advertising it into BGP? Okay. If none of our routes have a next hop address of 0.0.0.0, it then prefers the shortest autonomous system path. Okay. Again, AS path, if you don't change any attributes, a lot of times the autonomous system path is what's going to determine what is the best path to reach a destination network. Okay. And they show only the length is compared. What they're talking about, how many total autonomous systems. Okay. I see autonomous system number 1, just like I see autonomous system number 65,500. Okay. There's still just one autonomous system. Even though there are more numbers than 65,500, still just one autonomous system. Okay. If we have the same length of AS path, then it would prefer the lowest origin code. Now we're seeing, how did this route get into BGP? And we would prefer an I over an E over a question mark on how that route was actually put into BGP. If that route happened to have the exact same origin code, then it would prefer the lowest multi-exit discriminator value. Okay. Like I said, that's that metric value that we're looking at there. If neither one of these two have a med value, then it would prefer an external BGP path over an internal BGP path. Again, makes sense. Send it out onto my service provider rather than sending it to another internal neighbor to go out. Okay? Why not use somebody else's bandwidth rather than using my bandwidth, my own autonomous system? If both of our paths are internal BGP paths, so I learned them from 2 different internal BGP neighbors, I would then prefer the path through the closest IGP neighbor. So now we're looking into OSPF or EIGRP. Which one of those is the closest neighbor to us? Okay. If both of the routes are external BGP learned, then they would prefer the oldest or most stable path. Okay. Just simply, which one did we learn first? It's just at least some way of being able to prefer one path over the other. Now, if we happen to learn both those eBGP routes at the exact same time, slim to nil, but it could happen, right? They show we would prefer the path from the router with the lowest BGP router ID. Now, maybe I learned the path at the exact same time from the exact same router. So we've got something like this. My autonomous system connected outbound to ISP number 1. We got my router, the service provider's router, and we have 2 links in between those 2 routers. I might have learned one route through this interface and one route through this interface. Well, then it would prefer the path with the lowest BGP IP address, right? So it'd just simply be looking at what is the IP addresses on these 2 interfaces, which one's the lowest address of that neighbor. Okay. So there's always a way of being able to break a tie. This is very, very important when you start looking into BGP. How does it use those BGP attributes? Okay. So I've got about 10 minutes left. Are there any questions? Well, if there aren't any questions, that's kind of what I have for you guys for this particular section here. Hope you guys can show back up at, let's see, I'm pretty sure it's from 10 o'clock to 11 o'clock Mountain Time. I'm going to go through and talk about configuring BGP. So come back to another tech talk with me.
Quick question.
Yeah, go ahead.
Yeah, so since BGP doesn't load balance, what would be the best method to inject another quad 0 route into the routing table?
So usually people use their internal network or internal gateway protocol for that. Does that make sense? Let me explain. It's a great question. Just going to get something that I can actually draw on here a little bit better. So if this is my autonomous system out over here, right, we'll call it AS 65000, for instance. And I've got, let's say, router number 1, router number 2. They're connected outbound to ISP number 1. We got ISP number 2. Okay. You may have an internal BGP peering session between router number 1 and router number 2 within here. We've got external BGP outbound to my service providers. But to the rest of the network in here, right, we're using an internal gateway protocol, something like EIGRP, for instance, or OSPF, okay? So in that case, one of two things that you could do, depending on whether or not you're using OSPF or EIGRP. In OSPF, we're gonna learn a route via BGP, and on both router number 1 and router number 2, we're gonna do what they call a default information originate, okay? In OSPF, that would advertise 0.0.0.0/0 outbound. Okay, you do that same thing over here at router number 2, they would advertise a 0.0.0.0/0 outbound in OSPF. In EIGRP, we would typically redistribute that default route, okay? Now, as I learn the route via BGP, I can create a route map that matches that all zeros route, and I can redistribute that in EIGRP at that point in time. So I'd say, redistribute BGP going through this route map called default only, for instance. Does that make sense?
Yep, I should have probably worded my question better. If you're in a private IP network and say you don't have a router 2 and you swing that ISP, that private IP into router 1, so you have 2 PIP circuits, then yep, there you go. How would you manipulate, since it doesn't load balance, how would you inject those 2 routes so they could not be
So
load
again, are you talking about into OSPF so that my other routers that we have in my autonomous system have multiple default routes?
Nope, I'm talking within BGP routing table. So it says, how do I see both?
Well, I'm going to learn both, right? I'm still going to learn one from ISP number 1 and learn one from ISP number 2. So in my BGP table there, router number 1, you will see 2 different default routes. One will be preferred. That's the only difference. Right? And as far as into the rest of my autonomous system, again, the default information originate would advertise the default route. These guys, let's say router number 3 out over here, only needs one default route to get to router number 1. And then it's router number 1's choice. Do we use ISP number 1 or ISP number 2? Does that make sense?
Yeah, I was thinking more on max path 2.
Sure.
Man.
Or we're looking at specific routes, right? Because you don't have to just get default routes from your service providers. I can get full internet routing information and have router number 1 determine based off of what the destination IP address, what route does that match, and should I use ISP number 1 or ISP number 2 as kind of an active type of situation. Okay, but if all I'm doing is receiving default routes from my service providers, one of those default routes is going to be preferred route in BGP. Now, you can go through and enable now BGP multipathing, which could then load balance those 2 different default routes as well, okay? Just let you know, it's just not enabled by default. But newer implementations of BGP allow for what they call BGP multipath that can actually go through and do load balancing on multiple default routes as well. Does that answer your question then?
Yes.
Perfect. Alrighty then, I'll let you guys go. Thanks for coming in.